Hello and welcome everyone. My name is Hannah Mason and I'm a technical editor at Composites World. I want to thank you for joining us today for this webinar titled Troubleshooting Prepreg Cure Failure Modes with Rheological Measurements, brought to you by Composites World and presented by Alpha Technologies. Understanding the complexities of curing prepregs is crucial in composite material research. In this webinar, Alpha Technologies will discuss an in-depth study exploring prepreg cure failure modes, as well as highlighting optimal conditions and presenting insights into cure states and viscosity levels, aiming to further the reliability and performance of composite materials. Here to talk about this subject today, we have our presenter, Ünal Yilmazoglu, Applications Engineer at Alpha Technologies. Ünal has over a decade of polymer experience, beginning in research laboratories where he served as a research scientist, developing his theoretical knowledge and practical expertise. In his current role, he specializes in the development and implementation of rheology solutions as an expert in polymer science. And without further ado, welcome, Ünal. It's all yours.
Awesome. Thank you very much for the kind introduction. I know today's topic, or should I say today's title, is quite a mouthful: troubleshooting common prepreg cure failure modes with rheological measurements. It might even make you wonder if there's going to be a quiz afterward, but don't worry. My goal is to make it as clear and straightforward as possible. So I'll walk you through what we have achieved using rheological measurements to optimize prepreg curing step by step. So here's the plan. We will start with why prepreg curing matters and look at some methods for studying it. Then we'll dive into the key factors that influence prepreg curing. And after that, we'll get into the experimental section where I'll discuss the materials that we tested, and then how we prepared the samples and how we use the encapsulated sample rheometer, or ESR, to gather data. Next, I will introduce a novel analysis method called G-prime rate analysis, which offers a new way to understand curing behavior. And finally, we'll walk through these results and see how each factor, temperature, ramp rate, pressure, and layup orientation, affects the curing process. All right, let's start with prepreg curing and key factors. So prepreg materials are a combination of fibers which provide reinforcement and resins, technically, which bind everything together. And when the resin cures, it forms strong chemical bonds called cross links. This boosts the material's strength and performance, which makes it suitable for various applications, including aerospace and space applications. And you can think of it like gluing two pieces of wood together. If the glue doesn't cure properly, the bond is weak and the pieces will eventually separate. And again, rheology is our friend. It can be a bit of boring friend when it comes to data analysis, but it is the kind of friend who always shows up with the answers you need. And let's look at how rheology helps us analyze curing behavior of prepregs. There are a few different ways to analyze rheological data. For example, some researchers focus on G-prime, elastic modulus, which we'll emphasize today. Others use G double prime, or viscous modulus, or tangent delta, the ratio of G double prime to G prime. For this discussion, G prime will be our hero. Why? Because it gives us a clear understanding of how the material transitions from liquid to solid, essentially, how the resin crosslinks and cures. Let me break this down for you. If you look at the orange curve on the graph, you'll notice something interesting during the first temperature ramp. This phase, often called the first soak, is critical. It melts the resin and allows it to flow properly through the fibers, creating a strong and reliable matrix. Then, as we ramp up the temperature further and hit the cure temperature, TC, you'll see a sharp increase in G-prime elastic modulus in the orange curve. This sharp rise indicates that the curing reaction is happening, with the resin cross-linking and becoming more solid. Eventually, the curing reaction slows down and terminates, which we see as G-prime leveling off to a plateau. If you think of it, G-prime as a mirror that reflects the material's solid character, it makes perfect sense that it increases dramatically during curing. And after all, as the cross-linking progresses, the material becomes more solid, reaching much higher values of G prime compared to its initial state. Rheology is also helpful for studying resin behavior on its own. That means we can test resins alone without impregnated in fibers, like during gel time studies. But today we're focusing on the full prepreg system where the resin and fibers interact. Proper curing is critical. It minimizes defects, prevents failures, and ensures the material performs as expected. Rheological analysis provides the insights and information needed to fine-tune these processes. And to study the curing process, we turn to our trusty companion, the ESR, our big friend in the lab. This powerful tool helps us measure rheology with precision and consistency, and it also complies with ASTM D7750 standards. It's like having a lab partner who never takes a coffee break. Let's talk about the major factors that drive the curing process: cure temperature, temperature ramp rate, pressure, out time, and layup orientation. We'll explore how each of these factors impacts the curing process in the results section shortly. Okay, let's move on to the experimental section. If we take a closer look at our dear friend ESR, the encapsulated sample rheometer, as the name suggests, the encapsulated part comes from its closed cavity design, which makes it perfect for precise rheological measurements. And this instrument operates across a very wide range of conditions for the temperature range from ambient, basically your factory air temperature, up to 350 degrees C, and a strain range from 0.07% to 1256%, covering everything from tiny deformation to significant loads, and frequency, which ranges from 0.0016 Hz to 50 Hz, allowing us to perform not just cure tests, but other dynamic tests as well. And also the torque range from 0.02 decNewton-meter to 240 decNewton-meter, making it ideal for handling even stiff materials. On the right-hand side, you will see a typical cure temperature profile, sometimes called a cure cycle or Cook cycle. On the y-axis, we have temperature, and on the x-axis, we have time. The process starts with a first heating ramp, R1, done at 2.5 degrees C per minute. This stage holds the temperature below the cure point, allowing the resin to flow evenly and sometimes helps removing some bubbles, ensuring a uniform matrix. And this stage is often called soak stage or the well stage. Next, we ramp the temperature up to the cure temperature, known as the second heating ramp, which is the R2. And here, the curing process happens as long as we heat the cure temperature, and we hold at this temperature for a set period. Finally, the sample is cooled with a ramp rate of 3 degrees C per minute. On top of that, the ESR allows testing in oscillatory shear mode. For this study, we used a strain of 0.7% and a frequency of 0.667 Hz, which is quite static to gather the data. Okay, let's shift our focus to materials involved in this study. And then to make things easier, I've included the cure profile on the right-hand side as a reference, especially since we'll be diving into some specific variables. We work with two types of prepregs. The first one is the P1, the woven fabric, and this material was held at 60 degrees C for 10 minutes to ensure proper resin flow in the duvel stage. Following this, the temperature was ramped up using R2, a variable ramp rate we studied to see its impact. Once the cure temperature was reached, the material was held for 90 minutes or 1.5 hours. Again, we are going to see the effect of cure temperature shortly, and then cooled down with a cooling rate of 3 degrees C per minute. The second material, P2, is unidirectional tape. The hold temperature for this material was around 121 degrees C with a hold time of 10 minutes for resin flow. The second ramp rate to the cure temperature was fixed at 2.5 degrees C per minute, and we cured the material at 177 degrees C for roughly 2 hours before cooling. What is unique about P2 is that the only variable we changed was the layup orientation. We tested 3 orientation, 0 degree, where all fibers align in one direction, 90 degree with fibers perpendicular to each other, and 45 degree. Just to keep in mind that orientations other than 0 degree is referred to as sometimes quasi-isotropic stacking, another fancy name. Okay, now let's talk about the sample prep method and what we like to call the cut, stack, and seal approach. And here's how it works. First, you cut the pre-preg samples using a cookie die cutter. Then you stack the cut pieces on top of each other to reach the desired thickness. And finally, you seal the stack with a patented O-ring to make sure everything stays in place for testing. And that's it. The process is simple and doesn't require any fancy equipment or elaborate preparation. In fact, the entire sample prep typically takes just 5 to 10 minutes. And once you practice, you can probably shave off a couple of minutes. And then once your sample is ready, all you need to do is place it on the rheometer and press a button to start the test. That's it. Just prep, place, and go. Before we move on to the results, let's dive into the G-prime rate analysis step by step. And we propose here, this way of looking at the data provides some significant understanding for curing process. Instead of just looking at G-prime directly, here we are analyzing the G-prime rate, which is simply the first derivative of G-prime. So what does that mean? Essentially, we are focusing on how G-prime changes over time, whether it is increasing, staying constant, or decreasing. And here's what we observe. Initially, when we ramp up to the hold or soak temperature, we don't see much change in G-prime. This is because we haven't hit the cure temperature yet. Once we hit the cure temperature, there's a drastic increase in the G-prime rate. The curing reaction kicks in, and G-prime rate starts to climb rapidly and reaches its maximum. And then, as a reaction progresses, the G-prime rate decays and eventually reaches 0, signaling that the system has stabilized and G-prime has reached its plateau, so we don't expect to see any change in G-prime. And then in the cooling step, which is the second bump over there, during cooling, there's a slight increase in G-prime as the material stiffens. This happens naturally as the material cools and reinforces its structure, eventually drops down again. Here's the fascinating part, maybe the boring part. We can define 2 time intervals to better understand this behavior, delta T alpha and delta T beta. I know we could go for something more creative or fancy, but keeping it straightforward with alpha and beta makes it easier to follow and focus on the key concepts. Sometimes simplicity is the best choice. All right. Delta T alpha is the time interval for the start and progress of the curing reaction, while delta T beta is the phase where the curing reaction slows down and terminates. Here's why these intervals matter. A smaller delta T alpha means the material reaches the maximum cure rate more quickly, indicating a faster curing initiation. A smaller delta T beta means the curing reaction stabilizes faster, allowing the system to reach equilibrium sooner. The ideal cure cycle we propose should exhibit both delta T alpha and delta T beta as short intervals. Actually, we prefer balancing these two since homogeneous cure dynamics is quite important. For example, when optimizing the cure temperature, we aim to minimize delta T beta to check if undercuring or overcuring is happening. Overcuring sometimes can lead to unwanted changes in material properties, so achieving a quick delta T beta and adjusting the process parameters based on that reduces cost and is really significant for efficiency and quality. Are you excited to see the results? Okay, let's dive right in. First, let's look at the effect of cure temperature. For this experiment, we cured the woven prepreg P1 at 6 different temperatures with roughly 2 degrees C intervals. If you look at the G prime versus time plot, which shows a typical cure curve for prepreg, you can clearly see that the final G prime values are affected by the cure temperature. At the end of curing, just before cooling, the G prime varies for different temperatures, highlighting how temperature influences the material's stiffness and cross-linking behavior. Now, if we switch to the G prime rate plot, here's what we notice. All temperatures begin curing at roughly the same time. However, at higher temperatures, such as 132 degrees C, the delta T alpha is much shorter. This means the G prime increase happens much more rapidly, which makes sense because higher temperatures typically accelerate the cure reaction. And as the reaction progresses, all temperatures eventually stabilize with the G prime rate reaching 0. What is interesting is that when we compare the delta T beta across these temperatures, we find that the 127 degrees C has the lowest delta TB or beta, indicating a faster stabilization phase. And this suggests that 127 degrees C may be the optimal cure temperature for this system, which balances rapid curing with controlled stabilization. And one of the most common and fundamental questions in pre-preg curing is, am I ramping up too fast or too slow? Let's look at what the data tells us. If you remember from very first slides, essentially, R2 is how quickly we reach the cure temperature after the first soak or dwell stage, right? In this study, we tested 5 different ramp rates for woven pre-preg: 1, 2.5, 5, 10, and 20 degrees C per minute. This wide range allows us to see how different ramp rates affect the curing process. And for this study, we kept the cure temperature constant and consistent, only the ramp rate was varied. Here's what we have found. With 5 degrees C per minute, we observed the shortest delta T alpha and delta T beta, suggesting that this rate may be near optimal for this resin system. This likely happens because at this rate, the resin flow and cure kinetics are balanced, allowing the cross-linking process to proceed more efficiently. The result, a higher G prime at the end of curing, which indicates improved cross-linking density. This, in turn, suggests stiffer and potentially stronger material properties compared to other ramp rates. So for this system, 5 degrees C per minute might strike the best balance between cure speed and final product performance. Now, let's take a look at the pressure study. In this experiment, we adjusted the pressure on the sample by changing the air cylinder pressure within the test. We tested materials under 3 different cylinder pressures: 50 psi, 70 psi, and 90 psi. And to keep the things consistent, the ramp rate and cure temperature were held constant. And here's what we observed. There wasn't a significant difference in the G prime at the end of cure between 50, 70, and 90 psi, although 70 psi showed a slightly higher G prime compared to the others. The real insight comes from the delta T alpha and delta T beta values. As pressure increased beyond 70 psi, 2 things happened. First, delta T alpha and delta TB increased significantly, meaning that the curing process took longer to initiate and stabilize. The second, the final G prime value decreased, suggesting a weaker material structure. This trend could be linked to the excessive pressure may cause resin starvation, where the resin is squeezed out, leading to some dry spots in the material. And these dry spots highly likely weaken the matrix and reduce overall performance. So in a nutshell, too little pressure might not consolidate the material effectively, but too much pressure can compromise resin flow and performance. And for this system, 70 psi seems to strike the right balance for achieving the best curing performance for woven pre-preg. All right, we are almost at the end, but before the final study, let's talk about the out time. In this study, we examined how leaving the prepregs out for extended periods impact curing. The prepregs were left for 3, 6, 9, and 12 days, and then we tested afterwards. If I remember correctly, the relative humidity was between 50 to 60%. Here's what we have found. For up to 12 days, the material's properties didn't change significantly. In fact, at 9 days, we observed the optimal G prime at the end of cure, along with the lowest delta T alpha and delta T beta. This shows that the woven prepreg is relatively robust and can tolerate extended out times. However, at 12 days, things started to change. The G prime at the end of cure decreased, while delta T alpha and delta T beta increased, signaling there's something probably going on, and this may be your maximum tolerance for leaving your prepreg without storing in a freezer. However, generally, prolonged exposure to air can lead to moisture absorption, which affects curing and can cause defects like bubbles or, in other words, voids. So keep in mind that. Finally, we reached the last study for prepreg curing. In this study, we introduced PTU, which makes its first and final appearance here. The focus was on the layup orientation, 0 degree, 45 degree, and 90 degree. This was done primarily to investigate how anisotropy affects curing behavior. Looking at the inside of the figure, we don't see significant differences in the G prime at the end of cure. However, the 45 degree layup orientation achieved the highest G prime at the end of cure, which is often expected. A 45 degree quasi-isotropic layup typically results in a more robust and balanced material. And one interesting observation comes from analyzing the anisotropy reflected in the curves. At 90 degree, the bimodal curve tilts to the left, and at 45 degree, we see a perfectly symmetrical bimodal curve, and for 0 degree, the bimodal curve tilts to the right. And this pattern highlights how the orientation impacts curing behavior for unidirectional tape. By analyzing the G prime rate, we can also troubleshoot whether the intended 45 degree layup orientation was effectively achieved or if adjustments are needed. So let's wrap up. Rheological measurements gives us a significant understanding of how various factors such as cure temperature, ramp rate, pressure, out time, and layup orientation influence the curing behavior of prepregs. Each of these plays a critical role in the final product. The ESR is a powerful instrument in this process. It not only supports the process and product optimization, but also helps troubleshoot common failure modes that we have already covered, even when the differences are small.